progress. Good morning, everyone.
Morning, sir.
Can you able to see my screen?
Yes, sir.
Yes, sir.
Fine. Yeah, last class we had some problem with PPT, so just we can revise it very shortly. Then we will move on to the topic. Okay. Here it is a unit cell. This is a unit cell. It's a single part. It's a kind of building blocks of an entire crystal. Suppose it is the smallest portion of a crystalline, which when repeated in different direction and generate an entire crystal. Say for example, it is a building block of crystal. The first unit cell will be attached to the second one, and next will be bottom of this one, then right of this one, then front of the first unit cell and bottom of the second unit cell. Okay, so now we have a unit cell. So I can't made it 8 unit cell in this because we can't able to see that. So now you can assume that it's a L-shaped box, right? L-shaped box. So this is one unit cell, first unit cell, second unit cell, third unit cell, fourth unit cell, fifth unit cell, sixth unit cell. So likewise, in this front, we have one unit cell. In this bottom also, we have one unit cell. Now we can consider this one atom. This one corner atom is shared with 7 different unit cells. Totally 8 unit cells. Is that clear? Is that clear or not?
Yes, sir.
If I'm taking this corner atom, just if I'm taking this corner atom, along with that, we have top of this, right of this, bottom of this, left of this, front of this, back of this. We have many unit cells. Okay, so each and every corner atom contributes its 1/8 part for its particular unit cell. For this particular first unit cell, its contribution is 1/8. For that second unit cell, it's 1/8. Likewise, it's 1/8. Totally one atom. One atom is shared by 8 parts for different 8 unit cells. Okay. So first we can make like this. After that, the entire crystal will generate. Okay, this is a crystallite, and now another crystallite will attach. So it forms crystal-like structure. So it forms crystals. Okay, many crystallites, small crystallites, then can combine to form a big crystal. Okay. The next one is a unit cell is characterized by 6 parameters we already discussed. 3 edges and 3 angles. A, B, C are the edges, and alpha, beta, gamma are the angles. We know that this is A, this is B, and this is C. And B, C, it is alpha, and it is beta, and this is gamma. We discussed. If A equal to B equal to C and alpha equal to beta equal to gamma, that is equal to 90 degrees. If it's a simple cubic. Suppose if a cube is like this, here A is different, B is different, C is different. Okay, because the length is different. B is somewhat bigger length. C when compared to C. C when compared to A and B, A and C, B has more length. That's what A not equal to B not equal to C, but at the same time alpha equal to beta equal to gamma, that is equal to 90 degrees. The angle between them are equal to 90 degrees. Based on this, so the unit cell can be characterized by 7 lattice system. One is cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, then rhombohedral. Simply we can remember it. C Tom T H R. C Tom is there. Okay, you can assume it. C Tom is there. C means C. T, that is cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. Okay, you can simply remember all those things. C Tom is there. C Tom THR. Okay. These are all the 7 lattice system. Let's discuss one by one. The first one is cubic. We know that A equal to B equal to C, but alpha, beta, gamma all are equal to 90 degrees. We know that here I can assume it. This is the ABC. AH lenses ABC, and alpha between alpha, beta, gamma all are equal to 90 degree. Then it forms simple cubic unit cell. Tetragonal. So A equal to B, but B not equal to C. So you consider this is A and this is B, and the entire thing is C. Okay. So we know that A equal to B, but not equal to C. But alpha, beta, gamma equal to 90 degree. Then it is called tetragonal. Orthorhombic, here also almost A not equal to B not equal to C, but angle between them are equal to 90 degree. So this is A, this is B, this is C. This is the orthorhombic unit cell. Okay. In this unit cell, the edge lengths are not equal, but angle between them alpha, beta, and gamma are equal to 90 degree. Then it is called orthorhombic unit cell. The next one is the monoclinic. Monoclinic, actually it's not like that 120 degree, not equal to gamma, not equal to 90 degree. Okay. So monoclinic, this is the monoclinic structure. Here also the same A, B, C. So A, B, C, that is edge lengths are not equal, but angle between them or two angles are equal, but one angle is not equal.
Sir,
Triclinic,
sir,
yes,
sir, monoclinic alpha is equal to gamma, right, sir?
yeah, alpha equal to gamma. Fine. Alpha equal to gamma equal to 90, then beta not equal to 90. Why? Because this is alpha, beta. And sorry, this is gamma, this is alpha, this is beta. Okay, alpha, beta, alpha, gamma are equal, but beta is not equal. Very good. Then triclinic, A not equal to B not equal to C, but alpha, beta, gamma not equal to 90 degree. Nothing is equal. Then it is triclinic unit cell. Hexagonal. So this is the hexagonal unit cell. Here we have to look at this black color only. So here it is the edge length A, B, and C. Angle between them gamma, alpha, and beta. So alpha equal to beta equal to 90 degree, but gamma equal to 120 degree. Then it is called hexagon. Here also A equal to B. A and B are equal, but C is not equal. Then rhombohedral. Here also A equal to B equal to C. Alpha equal to beta equal to gamma, but exactly not equal to 90 degree because it's a tilted cube. Tilted cube like structure. So the angles may differ, but edge lengths are equal. Okay. Yeah. So unit cell categories. So we know that a primitive unit cell, and it is not canted, it's centered unit cell. Centered unit cell. So primitive unit cell is what? Atoms are only at corners. But centered unit cell, apart from the corner, they have atoms are somewhere else also present. Okay, that is what is centered unit cell. So here it is an example of primitive unit cell. It has 8 corners. 1, 2, 3, 4, 5, 6, 7, 8. So totally 8 corner atoms are there. This is a 3-dimensional representation of this one. So if it has 6 faces and 8 corners. Okay. This is a primitive unit cell. Atoms are only located at corners. But in reality, it will not be like this. Okay. In reality, all the atoms are touching together. Each and every atom will touch together. But for the understanding, they are giving like this. In reality, this will be like this. Each and every atom will touch together. Okay. The reality will be looking like this one. But for the understanding only, they given like this. Then centered unit cell. In this centered unit cell, we have 3 more categories. Just a minute. Just a minute. 1 minute. I'll come. Okay, no, very sorry. So then centered unit cell, we have categories: body centered unit cell, then face centered unit cell, then end centered unit cell. We know that this is a body centered unit cell. This is a BCC structure. So the entire whole body, one atom is located. The blue color atom which is located inside the body, okay, which is not going to share with any other unit cell. Okay. So this is a body centered unit cell. So here also 8 corner atoms and 1 center atom exclusively for this particular unit cell. And this is a face-centered unit cell. We know that it is a 8 corner atoms and 6 face centers are there. So while you're looking in 2 dimension, it will be looking 1, 2, 3, 4, 5 only is there. But back of this we have 1 more atom. So it will be looking like this. Okay. So there are 6 faces are there. So each face-centered atom contribution will check. This is the face-centered unit cell. Yeah, next one is a end-centered unit cell, either top, bottom, or left, right, or front, back. Okay. So in this, any of the 2 places, any of the 2 center is occupied by 2 atoms, then it is called end-centered. It will be like looking like this. Okay. And next one is a Bravais lattice. Bravais lattice refers to the 14 different 3-dimensional configurations into which a constant particles can be arranged in a crystal. So based on this arrangement, based on this atoms arrangement, there are only 14 possibilities. It is experimentally found out. So he given 14 different unit cells. So only 14 different unit cells is possible. Okay. So by the way, they given cubic unit cell which consists of primitive, body centered, face centered. Then tetragonal, it has primitive and body centered. Then orthorhombic has all the 4, that is primitive, body centered, face centered, and end centered. Monoclinic, primitive, end centered, and triclinic, hexagonal, rhomboidal, everything is primitive one. Okay. So this is about a Bravais lattice. In this Bravais lattice, we can discuss what is a unit cell. This is primitive, right? Only atoms are located in corners. Okay. And we know that A equal to B equal to C, alpha equal to beta equal to gamma, that is equal to 90 degrees, that is cubic. Okay. And second category is what? Body centered. This is body centered unit cell. Okay. And third category is FCC, face centered unit cell. There are 3 categories of it. In tetragonal, we have first category is primitive. So only primitive is there. We know that angle and edge length is. So this is a primitive unit cell which consists of atoms are only located in corners. Next one is body center, BCC. So atoms are located in corners. Along with that, one exclusive atom is present in the body. Okay. And next one is orthorhombic. Orthorhombic, we have all the categories. There is primitive, body centered, primitive, body centered. Next one is a face centered, FCC, and also end centered. This is end centered. Okay, these are all the things. We'll have orthorhombic. Orthorhombic structure, we have orthorhombic unit cell will have all these possibilities: primitive, body centered, face centered, and monoclinic.
Sir,
Yes.
in cubic also we can have end-centered, no, sir?
Cubic also ends are not possible. Ends is not possible. Only simple cubic.
Sir?
Simple cubic in the sense that is experimentally found, man. So simple cubic only gives a primitive one.
Okay, sir.
Okay. The next one is yes, yeah, already discussed. I think so. Just a minute. Cubic unit cell, we have 3 categories: primitive, body centered, face centered. Not end centered is not possible. The arrangement is not like that. Only orthorhombic will have all the 4 possibilities. Then monoclinic, it will be like this, only primitive as well as end-centered. Primitive and end-centered unit cells. The next one is triclinic, only primitive. Primitive is the only case possible. Then hexagonal, here also only primitive is possible. Rhombohedral, here also primitive is possible. Okay. So totally we have 14 categories. 14 Bravais lattice is possible. Okay. And the number of atoms per unit cell is a simple cubic concept. So we know that number of atoms per unit cell. For this particular unit cell, we are going to calculate how many number of atoms are present inside the unit cell. Right. This is the second unit cell, third unit cell, fourth one, fifth one, sixth one. We already discussed about that. So if you taken this corner atom, it will be shared by, now it is 6 unit cells. Yeah, 6 unit cells. Right. If you have 1 unit cell here, if you have 1 more unit cell here, totally 8 unit cells. So one corner atom is shared with 8 different unit cells. So what about its contribution for this particular unit cell? Its contribution is 1/8 part. Is that clear? Is that clear or not?
Clear, sir.
Yeah. So say for example, you consider this is an atom. The atom is shared with 8 different unit cell, and this is for 1 unit cell, and this is for 1, 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 and this is for 1. So for particular unit cell, its contribution is 1/8 only. Each is 1/8. So totally we have 1 atom. So the entire 1 sphere is shared with 8 different unit cells. So now we have how many spheres? 1. So here we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 spheres are there. 1 sphere contribution for particular unit cell is 1/8. So totally 1 atom. Is that clear? So 1 atom per unit cell. So if you look at in 3 dimension, so one part, there is 1/8 part. This is also 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 1/8. This is also 1/8. This is also 1/8. Now you can have a question. So only 7 atoms are there, sir. One it is that means opposite to this one, or opposite to this one, or below this one. Okay, because in 2 dimension we are unable to visible it. Okay, so totally 8 corner atoms are there. Each corner atom contribution is 1/8. So number of atoms per unit cell is 1. Okay, and number of atoms per unit cell for BCC system. So this is a first unit cell. Here we have a corner atoms 1, 2, 3, 4, 5, 6, 7, 8. Each corner we have atoms. And entire center of this, I have 1 more atom. Suppose if I am placing another unit cell near to it, what will happen? Here also the corner atoms are there. Corner atoms are there for this particular unit cell. And corner atom contribution is 8 corner atoms. 1 corner atom contribution is 1/8, we know that. Plus, but entire 1 complete atom which is located inside of 1 unit cell. Is it sharing with any other unit cell? Corner atom shared with 8 unit cells, but center atom is it shared with any other nearby unit cells?
No, sir.
No. So then complete 1 atom is present. So totally 2 atoms. 2 atoms per unit cell. Is that clear?
Clear, sir.
So this is all about this body centered unit cell. So 8 corner atoms are there. 1 corner atom contribution is 1/8. Each corner atom 1/8 contribution. 1/8, 1/8, 1/8, 1/8, 1/8. Okay. Along with that 1 atom, that is a green color atom, which is located exclusively inside the body. which is not shared with this in particular nearby unit cell. And it does not share with any other units. That is what complete atom is located inside the body. So it will be taken as one full atom. So total is 2. So 2 atoms per unit cell.
Sir,
Sir, I have a
Yes.
doubt.
Yes.
Sir, suppose a unit cell is at the surface of a compound, sir, then the front
Okay.
atoms will not share, right?
Front atom will not be shared means
Like it won't give itself to the other unit cells, right, sir? It's at the surface.
for example,
It won't be 1 by 8, right?
this one. Okay. Suppose if it has some surface, on that surface, yeah.
And that surface a unit cell is,
Okay.
then it won't share 1 by 8, right, sir? And the corners also, top right or top left unit cell.
It's not like that. It's not like that. Because in each and every corner it will be shared because it doesn't have any end. Doesn't have any end. The entire crystal. So and the overall crystal, that is a regular repeating pattern will be arranged completely. Okay, the regular repeating pattern will be continuously continued overall entire crystals. Okay, each and every atoms will be shared with 8 corners. Okay,
Okay, sir.
and
sir,
number of atoms. Yes,
sir, for the BCC, you calculated that number of atoms as 2 atoms per unit cell, no, sir? Is it for one
yes.
unit cell or it is the result of
It's
combined
for
2
one
unit
particular
cells, sir?
unit cell. For this particular unit cell, there are 2 atoms.
So
So
then,
we are
why did you draw
calculating per
2
unit
unit
cell
cells?
only.
So then, why did you draw 2 unit cells in the previous diagram, sir? What does that mean, sir?
Because for understanding, I'll give you, man. It is not able to sharing with other things. That is what. So if suppose if I written like this in a single unit cell, it does not share means what it share. You can't able to understand. That is what I'm putting this like this. Okay. If you calculate for this atom also, 8 corner atoms, 1 corner atom contribution is 1 by 8 and 1 full atom is inside the body. So totally it is 2 atoms. Okay.
Okay, sir, understood.
Okay, and the next you will get to understand. This is space-centered unit cell. Suppose one unit cell is here. Okay, so corner atoms. You know the corner atoms 1, 2, 3, 4, 5, 6, 7, 8. 8 corner atoms are there. Now we have one atom in face center. Okay, another atom in face center. There are 6 face atoms are there. Am I right? 6 face-centered atoms are there. It will be looking like this. So what about its contribution to the nearby unit cell? If I said simply, you can't understand. So if the share is 1 by 2, how you can understand? Just a minute. I'll show you. Suppose one other unit cell is there. Now you can have, for the better understanding only, I'm putting like this. Okay. Actually, it is present inside of this only. Yeah. If you have another unit cell, what about the share of this unit cell? 1/2 will be shared to this particular unit cell. Another half will be for nearby unit cell. So if it is a one body centered atom is there, what about its contribution? For this particular unit cell, 1 by 2. For this particular unit cell is 1 by 2. Is that clear? Is that clear or
Yes,
not?
sir.
Can you repeat once?
Yes, sir.
Yeah. So we know that face-centered cubic cell means 8 corner atoms and 6 face-centered atoms. So black colors are corner atoms and red colors are face-centered atoms. Okay. If you have one more unit cell with this, because we have not only have this front right of this, top of this, left of this, bottom of this, front of this, back of this. Every unit cell is surrounded by 7 other unit cells. Okay. So each and every unit cell contribution. Say for example, if I'm taken this unit cell, okay, if I'm comparing this first unit cell and second unit cell, these two unit cell, corner atom contribution is 1 by 8. We know that because it is shared with 8 other unit cells. But face centered atom sharing is 1/2. The atom 4 whole spheres divided into 2. 1/2 will be used for this particular unit cell and 1/2 will be for another unit cell. Is that clear? So one face centered atom contribution is 1 by 2 for this particular one unit cell. For this particular unit cell, by the one face centered atom, 1 by 2 is the contribution. Is that clear?
Yes, sir.
Okay. So 8 corner atoms are there. One corner atom contribution is 1 by 8 plus totally for single unit cell, how many face centered atoms? 6 face centered atoms. Am I right? Into one face centered atom contribution for this particular unit cell is what? 1 by 2. So totally this is 1 and 3. So totally 4 atoms per unit. If it is a 4 atoms, face centered cubic unit cell, 4 atoms per unit cell. For one unit cell contribution is 4 atoms. Okay. Now we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 corner atoms are there. One corner atom contribution is, we know that each and every corner atom contribution is 1 by 8. Right? Each and every red corner atoms are 1 by 8 contribution. Blue color contribution is for this particular unit cell 1 by 2. For the nearby bottom unit cell, it is 1 by 2. For the right unit cell, nearby unit 1 by 2, and for this particular unit cell 1 by 2. Top of this also 1 by 2. Another contribution to another unit cell is 1 by 2. Here also, if you break it into, so 1/2, another half. Is that clear? By that way, we have a 6 face centered atoms, right? So there are backside also we have one atom. Okay. So there are 6 face centered atoms. So 6 face centered atom, but one atom contribution is 1 by 2 for one unit cell. Okay. So then it is 1, then 3. So totally 4 atoms per unit cell. Is that clear or not?
Yes, sir.
Yes.
Then number of atoms in the unit cell. Now you can tell me how many atoms per this particular unit cell. What is a unit cell? It is a primitive or simple cubic. Am I right? Primitive or simple cubic unit cell. Okay. What about this one?
1 atom.
Body centered. What about this one?
Yes, sir.
Yes, sir.
Face centered. FCC. Yeah. Now you can tell me how many number of atoms per this unit cell? Primitive.
1 atom.
One atom.
1 atom.
Very good. Here,
2.
1
Sir.
2 atoms. Very good. What about face centered
4,
atoms?
sir.
4.
atom.
Okay. Let's accumulate in this tabular column. Simple cubic unit cell. 8 corner atoms are there. One corner atom contribution is 1 by 8. So 1 atom is there. And there is no atoms on faces and center. So total is 1. For BCC, it is looking like this. 8 corner atom. One atom is a contribution. One whole atom which is located inside the body. So which is not going to share with any other unit cell. That's what one full atom we have taken. So totally 1 plus 1 is equal to 2. Face centered atom. So as usual, number of atoms at corner atom contribution is 1 and face centered atom contribution is 3. Total is 4. If it is end centered, how it will be? End centered means what?
8 into 1 by 8 plus 2 into
Yeah,
1 by
8
2.
into 1 by 8 plus 8 into 1 by 8 we have put. Then next,
There are 2 atoms in place.
yeah,
Half is
either, no, 2 atoms, either top and bottom or left and right or front and back. Only 2 atoms are there. So 2 atoms are there. One atom, corner atom, one face centered atom contribution is, we know that is 1 by 2 for this particular unit cell, 1 by 2 for nearby unit cell. Okay. So 1 by 2. So totally 1 by 2 is the contribution. Totally 2 atoms. There is no atoms in the center. So total number of atoms per unit cell is 2. Is that clear? Is that clear or not?
Yes, sir.
Yes.
Yes.
Fine. Fine. Next topic is closed parking in 1 dimension, 2 dimension, and 3 dimension. So we know that whenever you pack in any manner, we have some space between them. Okay, the space is otherwise called as voids. We can say as void, the empty space. See, for example, if I am packing these 4 balls, 4 spheres, first sphere, second sphere, third sphere, and fourth sphere, and center of that we have some space. Am I right? Center of this, we have some empty space. Okay, this empty space, with this empty space only we can able to pack. So because the atoms are considered as spheres, okay, atoms are considered as spheres, that's what they have, these kind of empty spaces in between them. Okay, so based on that, how we can close pack this particles? You consider each and every sphere is a particles. Okay, so they are considered as identical hard spheres. It can be built up by in 3D by 3 steps. First one is a closed packing arrangement in 1 dimension. There is no problem at all. There is no dimension. Only 1 dimension is there. Only 1 row will be there. Okay. And in closed packing in 2 dimension, we have 2 ways to pack it, the particles. One is square closed packing. Square closed packing arrangement. Square closed packing. Another one is hexagonal packing. Hexagonal closed packing arrangement. So one is square closed packing arrangement in 3 dimension also. Another one is hexagonal closed packing arrangement. That is HCP structure. Okay, HCP structure. Okay. So let's discuss one by one. For 1 dimension, closed packing in 1 dimension. So 1 atom is there. So each and every atom will be located like this. There is no, only 1 dimension is there. So either 1 axis, either X or Y or Z. Okay. So here there is, it doesn't touch with each other. Okay. This is a 1 dimension. If you pack, there is a only way. Otherwise, we can pack like this. Okay. We can pack like this. Okay. So any other way we can pack like this. Anyway, 1 row will be there. Okay. Now here we have to calculate the coordination number. What is the coordination number? What is the coordination number for 1 atom? Suppose if I'm considering this particular atom, this will be directly touching with how many atoms? 2 atoms.
2 atoms.
So the coordination number is 2. It is nothing but number of neighboring atoms. Neighboring atoms or neighboring particles, you can say. Okay. So if you take any atom, it will be touching with only 2 atoms. Okay. So this is what a 1 dimensional pack. So by that way only we can pack it in 1 dimension. Close packing in 2 dimensions, square close packed structure. Square close packed structure, how it will be like this? It will be like this because it is 2 dimension now. So attached like this. Yeah. Now, can you calculate the coordination number here?
For which atoms, sir?
For any atom. So actually it is not going to end because it is
sir.
continuously
3 or
continued
4,
all the
sir.
phases. 4.
4.
4 is a coordination number. Is that clear? Suppose if I'm taking this atom, it is directly touching with this atom and this atom and top of this and bottom of this. Okay. If you're connecting all the centers, you will get a square like structure. That is what it will be called a square closed packed structure. Is that clear? if you're connecting all those things, all the touching atoms, the coordination number here is 4, and it is forming a square like structure. That is what they will be called as square close packed structure. It has a lot of gaps. Am I right? It has a lot of space. Is that clear? So it has many empty spaces, or they large empty spaces are here. Okay.
Sir,
Yes.
sir, I have a question, sir, in one dimension. So the starting atom will also have coordination number as 2, sir. The atom
Yeah.
which with the
Because
periodic.
you assume it because you are coming to the same day, because it is not ending up, so it is continuously continued. Okay, in all the directions will be continued. Okay,
Okay, sir.
so that is what the coordination number is 2 only for all the atoms. Okay. Then hexagonal close packing, hexagonal close packed structure. So if it is a square close packing, the similar layer will be attached like this. Am I right? Be attached like this only in a square close packing. But if you want to close it, hexagonal close packing, we are need of different layer. Okay. Why different layer? Because we have to pack it in different way. If you are taken another blue atom, it will be packing like as usual in the square close packing structure. But in hexagonal packing, we are going to place the one red color atom between the two blue color atoms. So now the atoms are placed in a staggered manner. In staggered manner, we are placing this. Okay. Now third layer, fourth layer will be like this. Okay. Now, what is the coordination number?
Six,
5,
sir.
sir.
Sir,
5. Okay. 5.
Six,
Any other?
6, sir.
6. Okay. 6. Okay. Any other? Any other idea? 6 only. Okay. Suppose if I am taken this atom, it is directly touching with 1, 2, 3, 4, 5, 6. If you connecting all these centers, you will get a hexagonal structure. That is what they will be called as hexagonal close packing arrangement. Here the coordination number is 6. Okay. So coordination number is 6. So now you can tell me which kind of packing is better, hexagonal close packing or square close packing? You can see
Sir.
hexagonal close packing. Why?
Sir, because intermediate space is there.
Intermediate space will also be occupied, so it has less space when compared to less empty space. Here it has a lot of spaces are there. Okay, if you're looking at the square close packing structure, we have a lot of empty space, but in hexagonal close packing structure only less when compared to this one. Okay, when compared to square close packing, hexagonal packing somewhat having less amount of empty space, which means that they are tightly packed. Okay, in staggered manner, they are tightly packed with each other. This is what will be taken in hexagonal close packing. Okay, when compared to these two things, hexagonal close packing is tightly packed. Tightly packed. With less space, less empty space. Less empty space. Here, large empty space are there. Spaces are there. But in the case of hexagonal close packing, there will be a less empty space only there. Okay, is that clear? Is that clear or not?
Yes, sir. Clear, sir.
Yes.
Then three-dimensional square close packing. Three-dimensional square close packing. If it is a square close packing, all the layers should be similar, right? All the blue color atoms should be taken. Second layer, third layer, fourth layer, if I'm putting like this. Now you can consider, if you want to form a cube, you consider these 4 atoms. 1, 2, 3, 4. Back of this also we have 4 atoms. Am I right? Back of this also we have 4 atoms. Is that clear or not? Is it visible
Yes.
or not? You're going to consider 1, 2, 3, 4, 5, 6, 7, 8. Totally 8 atoms you have to consider. Is that clear? It is forming one cube. Now you can consider these atoms only you are going to consider. It will be looking like this. Okay. So if you take this is A, this is also A, this is also A, this is also A. If you move with any direction, this direction or this direction or this direction or this direction, everything is same. Square close packing, all the direction we have similar kind of pattern will be there, but it contains large space. Is that clear? It contains large empty spaces between them. Is that clear or not? So both the layers are arranged perfectly in all the directions. Okay. Both the layers, all the layers, all the layers, both the layers in the sense, both the direction. In this direction, if you taken this like this, if you taken like this, or if you taken like this, okay, in each and every direction, all the particles are arranged perfectly in all the directions. Okay, simple cubic, it always form primitive. Okay, primitive only here, square close packing based. And next one is hexagonal close packing. Hexagonal close packing, we know that. So it is a staggered manner of arrangement, am I right? The first layer will have more gap or more space, and second layer which is going to fill the space of first layer. Is that clear? Now you consider we are going to place it like this. We are going to place it like this. On this particular, we are going to place one atom, one red color. Is that clear? Similar pattern of arrangement will be followed through the entire system. Is that clear or not? So now you look at here, we have a lot of empty spaces, lot of white colors inside of this blue color. Am I right? In between the blue color, we have a lot of white color spaces. If you close packed in certain manner, staggered manner in the sense what? So between these two, we are going to place one. That's it. Okay, staggered manner. Now the empty space, the white color space is very, very less. Am I right?
Yes, sir.
The second layer should be put it in the depression of the first layer. That is what it can hexagonal close packing somewhat is reduces the empty spaces. Is that clear?
Clear, sir.
Okay, just a minute.
Sir, what is the coordination number, sir?
In where?
In 3D hexagonal packing.
3 dimension, it is 12. 12 is the coordination number. We can't assume it. Okay, just a minute. 12 is the coordination number. Yeah, this is 3-dimensional hexagonal packing. We talk about this one. So it will be packed like this. So staggered manner. So in between the two blue balls, one red ball is inserted. Then it is called hexagonal close packing structure. If second layer put it in depression, then it will also close some spaces. That's what we can more tightly pack the layers of A and B. Okay. Now the next thing is void. What do you mean by void? Void is nothing but an empty space. Void is nothing but an empty space. Here we have two different type of voids. One is tetrahedral voids, another one is octahedral voids. Do you have any idea about this tetrahedral and octahedral voids? Tetrahedral and octahedral voids. Say for example, yeah. Do you have any idea? You can share. So initially we have some empty space. If I'm packing 3 atoms like this, above which there will be an empty spaces there. Okay, there is a empty spaces here. So just I want to remove the empty space. So what I can do? So I have to add one more atom on the top. Okay, on the top, I can add one more atom to close this empty space. Okay, suppose if you have taken 3 balls in your hand, so it will be arranged in a triangle manner. Therefore, suppose if you are placing one more ball on the top, now the empty space between the 3 atoms are getting reduces because one atom will somewhat gives its contribution. Okay, it occupies some space. So between that 4 atoms, the tetrahedron is formed. That is what it will be called as tetrahedral voids. Here octahedral voids, I'll explain you. Here you consider this is the first sphere, second sphere or second atom, third atom. So now we have an empty space in between them, all these 3. Am I right? So in between them, we have some empty space like this. Now we are going to close the empty space. It will not be completely closed because in this side, in this direction, and bottom of this also we have some space. Even you are closing with the tetrahedral voids, even if you are placing the tetrahedral voids, still we have some more empty spaces out there. We can't pack it with 100% empty space. Okay, we always have some empty space between them. Okay, suppose if I am placing like this, somewhat it is getting arrested. Some empty space is getting closed. Okay, but even in the side we can't close it. In this side we can't close it. In this side we can't close it. Bottom of this we can close it. Okay, even though bottom atom is present, that also contributes somewhere else. So how many, whatever the way you are placing, so there will be some empty space will be there. Okay, so if you look at in that is the top view and this is the front view. Front view we can say, so this is the first atom, second atom, third atom, fourth atom. Now we got a tetrahedron structure. Okay, so it's like to be a tetrahedron structure. That's what will be called as tetrahedral void. So now also between these 4 atoms we have some empty spaces between them. That empty space is otherwise called as voids. So it will be looking like to be a tetrahedron. 4 atoms are surrounding. Between that we have some space. That's what is called as tetrahedral void. Is that clear?
Yes, sir.
Yes, sir.
What about octahedral voids? There are 6 atoms are there. They are arranged like this. Okay, why there are 6 atoms, but why it is called as octahedral? Why it is called as octahedral? Octahedron means what? Now you consider this is a first atom, blue color atoms are second atom, and this is a third atom, this is a fourth atom. Okay. Now top of this we have one red atom, and bottom of this we have one blue atom. Now you can consider these are all the corner atoms, and one top atom is there, one bottom atom is there. Is that clear? Now we can connecting all those things. I can connect all those things. Can you imagine in 3 dimension? Can you able to imagine in 3 dimension? Top of that, how many faces? This is one face, back of this one face, this is one face, and front of this one face. Is that clear? Can you able to imagine this or not?
Yes, sir.
Is it imaginable? Now this is one face, back of this one face, front of this one face, and this also one face. Totally top of that 4 faces, bottom of this 4 faces. Totally 8 faces are there. That is what we call as octahedral void. Is that clear? Octahedral void. But total number
Yes,
of
sir.
atoms are 6. Yes, yes, please.
No, sir, I
Sorry?
said it's clear. Sir, I said it's clear.
Sir, can you say
Okay.
the total number of faces in octahedral voids?
Yeah. Total number of faces in octahedral voids are 8. Okay, octahedral means 8. Octa means 8. Huh? So 8 faces are there if 6 atoms are combined in such a manner. Okay. And tetrahedral void. How we can find the tetrahedral void? For this, let I'm assuming it is an hexagonal close packing only. Hexagonal close packing means we are in need of second layer also. Am I right? Because we are going to place that in a staggered manner. Okay. So here, if you consider this is a atom number 1, atom number 2, atom number 3, atom number 4, atom number 5. If you take any 5 atoms, so if I'm taking 5 atoms in the crystal. So it's a crystal, just be clear again and again, I'm telling you. So it is a continuous one. Front, back, top, right, bottom, left, every space, every direction, it will be continued. Okay. And here one atom, second atom, third atom, 4, 5, 5 atoms I have taken. How many voids are directly connecting with these? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that clear? So there are 15 voids if I'm connecting all the 5 atoms. If you consider the 5 atoms are touching with each other, it has only 15 voids are there. Am I right? Suppose if I'm placing tetrahedral void means what? How we can assume the tetrahedral void? One atom is here, second atom is here, and third atom is here, and the top of this we are going to place one more atom. Am I right? To arrest this space, empty space. Is that clear? So where I'm going to place it? Suppose you consider this a first atom, second atom, and third atom. And top of this, I'm going to place one more atom. Okay, just you can look at here. If I'm placing like this, one red color atom is placed like this. Okay, is that clear? Is that clear? Same arrangement. 1, 2, and third. 3 atoms are there. This is 1, 2, 3. Top of this, I have 4th atom. That is red color atom. Is that clear? If I want to arrest the force between the 3 triangles, that means one triangle. So just I'm placing one atom on that. Is that clear or not? Still you can't get it? Still you can't get it? If you can't get it, I'll repeat once again. No problem. Can I repeat?
Yes, sir.
Yeah. So this is the first atom. You consider in any 5 atoms, here, any 5 atoms you can take. Okay. If it is a tetrahedral void means what? This is the first atom, second atom, third atom. So this is the first atom, second atom, third atom. Okay. I'm going to place one red color atom on this top. Then only it forms tetrahedral void, because in this between that 4 atoms only we have some empty space. That empty space is otherwise called as tetrahedral void. Am I right? Just I'm going to place one more atom here to arrest this space. Which space? To arrest this void. If I want to arrest this void, I'm going to place one more atom on the top of these 3 atoms. So likewise, I'm placing. Okay. Is that clear or not?
Yes, sir.
Fine.
Sir, so
Then-
each red ball is a tetrahedral void for the respective blue ball, sir.
Yes. Each red ball. Say for example, if we taken any 3 atoms, suppose if I'm taken this atom, 1, 2, 3, and this is one red ball. Suppose if I'm taken 1, 2, 3, one red ball. For suppose if I'm taken 1, 2, 3 blue atoms, so I'm connecting all the blue atoms, then red atom. So the similar pattern will be followed. Okay, is that clear? It contains both tetrahedral, octahedral voids also. First you learn about the tetrahedral voids, then we can able to understand octahedral voids. Is that clear? Can you able to understand this?
Yes, sir.
Fine. Good, Kanan. Super. Right. Now some pores are not arrested. What are all the forces? These are all the forces. Am I right? Not arrested. Okay. These forces are not arrested. It's a O-shaped void. Now you can consider. So if suppose you consider how many atoms are there at the top. Say for example, now you can consider about this void. Okay. Okay, let us finish with the tetrahedral void, then we can have octahedral void. How many tetrahedral voids are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose if I am taken 5 atoms, how many tetrahedral voids are there? 10 tetrahedral voids are there. Is that clear? Suppose if I'm taken n atoms, 2n tetrahedral voids are there. Very, very important formula. Okay. If I'm taken any number of atoms, 2n number of voids will be there. Which void? Tetrahedral voids. Is that clear or not? Then we'll move on to next. Is that clear or not? I'm taken 5 atoms. So I rounded the number at 1, 2, 3, 4, 5. So I'm taken 5 atoms. How many tetrahedral voids are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 tetrahedral voids are there. Is it clear?
Yes, sir.
Understand பண்றதுக்கு ரொம்ப கஷ்டமா இருக்கா?
Able to understand, sir.
கொஞ்சம் கஷ்டமா இருக்கா? Okay, fine. அதுக்கு தாய்மொழி தான் பெட்டரு. வரேன். Okay. சோ நமக்கு தெரியும், அதாவது ஒரு பால் எடுத்துருக்கோம், இந்த மாதிரி க்ளோஸ் பண்ணிருக்கோம், பேக் பண்ணிருக்கோம். இந்த இடத்துல ஒரு வாய்ட் இருக்கு, கரெக்டா எம்டி ஸ்பேஸ் இருக்கு. அதை க்ளோஸ் பண்றதுக்காக தான் இன்னொரு ஆட்டம் இங்கே க்ளோஸ் பண்ணும். இப்படி க்ளோஸ் பண்ணாலும் இடையில என்ன இருக்கும்? சம் ஸ்பேஸ் இருக்கும். அந்த ஸ்பேஸ் பேர் தான் என்னது? டெட்ராஹெட்ரல் வாய்டுன்னு சொல்றோம். ஏன்னா 4 atoms are combined. அப்ப இங்க இருக்கக்கூடிய ஃபர்ஸ்ட் ஆட்டம் இது, செகண்ட் ஆட்டம் இது, தேர்ட் ஆட்டம் இது. அப்ப இந்த இடத்துல ஒரு எம்டி ஸ்பேஸ் இருக்கு, கரெக்டா? இந்த எம்டி ஸ்பேஸை க்ளோஸ் பண்றதுக்காக நான் என்ன பண்றேன்? ஜஸ்ட் ஐம் பிளேசிங் another layer like this. இந்த லேயரை பிளேஸ் பண்றேன். பிளேஸ் பண்ண என்ன நடக்கும்? இப்போ 4 atoms வந்துருச்சு, கரெக்டா? அப்ப இந்த என்டையர் திங் பாருங்க, இது எப்படி இருக்கு? இதே மாதிரி இருக்கும். சோ இது வந்து 1, 2, 3 அவ்வளவுதான். It forms tetrahedral. Is that clear? அப்ப tetrahedral void நடுவுல இருக்கு, ஸ்பேஸ் இருக்கு. நீங்க எவ்வளவுதான் இந்த டைட்டா பேக் பண்ணாலும் 3 ஆட்டம்க்கு இடையில இந்த 4வது ஆட்டம் வச்சாலும் இடையில என்ன இருக்கும்? there will be some space, empty space இருக்கும். அந்த ஸ்பேஸ் பேர் தான் என்னது? tetrahedral void அப்படினு. இது புரியுதா?
Yes, sir. புரியுது.
ஓகே ஃபைன். இதே பாருங்க, இப்போ நான் என்ன பண்றேன்? ஒரு 5 ஆட்டம் கன்சிடர் பண்ணிக்கிறேன். இப்போ இத மறந்துடுங்க. ஓகே, ஒரு 5 ஆட்டம் கன்சிடர் பண்ணிக்கிறேன். இந்த 5 ஆட்டம் எடுத்தா எத்தனை வாய்ட் இருக்குன்னு பாருங்க. இந்த 5 ஆட்டம் டச் ஆயிருக்கக்கூடிய வாய்ட்ஸ் 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. அப்ப மொத்தமா 15 வாய்ட் இருக்கு. நான் அந்த 5 ஆட்டம் மட்டும் கன்சிடர் பண்ணலாம், ஒரு சைடுல கன்சிடர் பண்ணலாம். சரியா? நான் ஜஸ்ட் அந்த 3 அந்த வாய்டை மட்டும் எடுத்துருக்கேன். இந்த 3 வாய்டை மட்டும் எடுத்துருக்கேன். சரியா? அப்படி எடுத்தனா என்ன கிடைக்குது? எனக்கு 15 வாய்டு கிடைக்கும். அந்த 15 வாய்ட்ல எத்தனை டெட்ராஹெட்ரல் வாய்டு, எத்தனை ஆக்டாஹெட்ரல் வாய்டுன்னு பாருங்க. ஃபர்ஸ்ட் டெட்ராய்டல் வாய்டு எவ்வளவுன்னு பார்ப்போம். டெட்ராய்டல் வாய்டுனுடைய அரேஞ்ச்மெண்ட் எப்படி இருக்கும் பாருங்களேன். இப்போ இது 1வது ஆட்டம், 2வது ஆட்டம், இது 3வது ஆட்டம். இப்போ இது மேலதான் வந்து க்ளோஸ் பண்ண போறேன். கரெக்டா? அப்படி க்ளோஸ் பண்ணா எனக்கு என்ன கிடைக்கும்? இந்த இடையில ஒரு வாய்டு கிடைக்கும், ஸ்பேஸ் கிடைக்கும். அந்த ஸ்பேஸுக்கு பேர் தானது டெட்ராஹெட்ரல் வாய்டு. அப்ப இது ஒரு வாய்டு, அப்ப இது ஒரு வாய்டு, இது ஒரு வாய்டு, இது ஒரு வாய்டு, இது ஒரு வாய்டு. அதே மாதிரி தான் இங்கேயும் பிளேஸ் ஆக போகுது. 1 2 3 4 5. இது அரெஸ்ட் ஆகாது, இது அரெஸ்ட் ஆகாது, இந்த வாய்டு வந்து அரெஸ்ட் ஆகாது. அது ஏன்னு சொல்றேன், அது ஆக்டாய்டல் வாய்டு. ஏன்னு பார்க்கலாம். இப்ப நான் சொல்றது புரியுதா? இப்ப லேயரை பிளேஸ் பண்ணீங்கன்னா எப்படி இருக்கும்? இப்படிதான் பிளேஸ் ஆகும். புரியுதா? அப்ப அந்த இதுக்கு முன்னாடி என்ன இருக்கு? எம்டி ஸ்பேஸ். இந்த ஒயிட் கலர் இந்த டாட் வச்சிருக்கேன் இல்லையா, இங்க டாட் வச்சிருக்கோம் பாருங்க, இந்த டாட் வச்சிருக்கோம் இல்லையா, இந்த டாட்ஸ் எல்லாம் வச்சிருக்கேன் இல்லையா, அந்த ஸ்பேஸ் வந்து எம்டியா இருக்குன்னு அர்த்தம். அது இப்ப நான் என்ன பண்ணிட்டேன்? அடைச்சிட்டேன், அதை வந்து க்ளோஸ் பண்ணிட்டேன். க்ளோஸ் பண்ணிட்டா எனக்கு என்ன கிடைக்கும்? இப்ப நீங்க இந்த ரெட் கலர் பார்ட்டிகளை வச்சுட்டு எல்லா பக்கமும் பாருங்க. இப்ப எனி ரெட் கலர் பார்ட்டிகல் யூ கேன் டேக். சப்போஸ் இந்த ரெட் கலர் பார்ட்டிகல் எடுத்துட்டேன்னா எப்படி இருக்கும்? இது ஒரு ப்ளூ ஆட்டம், செகண்ட் ப்ளூ ஆட்டம், தேர்ட் ப்ளூ ஆட்டம். அது மேல இதை பிளேஸ் பண்ணிடும். அப்ப அந்த 3 ஆட்டம்க்கு இடையில ஒரு ஸ்பேஸ் இருக்கும். அந்த ஸ்பேஸை க்ளோஸ் பண்றதுக்காக தான் இந்த ரெட் ஆட்டமே பிளேஸ் பண்ணிருக்கோம். அப்படி பிளேஸ் பண்ணாலும் என்ன இருக்கு? we have some empty space. அந்த ஸ்பேஸ் பேர் தான் என்னது? டெட்ராஹெட்ரல் வாய்டு. புரியுதா?
Yes, sir.
புரியுதா? புரியலையா?
Sir,
Yes,
so
sir.
normal void for a particular atom, we can take it as 3n, no, sir? For one
3 na?
atom, there will be 3 voids. You can take like that, no, sir?
Sorry,
3
I
void
can't get your
spaces.
question.
3 general void spaces will be there for one particle, no, sir?
Okay, what are all that?
Sir, here you marked 1, 2, 3, no, sir?
Yeah.
So we can take the general void for one atom as 3n, no, sir?
No, it's not for void. Is not for one atom. Void is for what is that? Structure, close packing structures. So we can't find a single void for atom. For an atom, we can't find out any void. If suppose
sir.
one atom is attached to this, one more atom is attached to, then only we can have some empty space in between them. Okay. Is that clear?
Okay, sir.
For a single atom, we can't find out any voids. So there will be an empty space between these three. That empty space is called void. So if you want to arrest this space, I can place one more atom. Okay. So still we have some empty space in between them. This is what it is called tetrahedral voids. Is that clear or not? Purida, Purilia. Purida, Purilia.
Little bit, sir.
Understood, friends.
Little bit.
Understood. Fine. Okay, super. Tetrahedral void புரியுது இல்லையா? அது அப்படியே octahedral void வரும். அப்ப tetrahedral void பாருங்களேன். 1 2 3. So லேயர்ஸ் பிளேஸ் பண்றேன். அதை ஏற்கனவே காமிச்ச மாதிரி தான் ஃப்ரண்ட் ஃபேஸ். அப்ப இப்பயும் ஸ்பேஸ் இருக்கும். சரியா? empty spaces will be there. That will be otherwise called as tetrahedral voids. Next பாருங்க octahedral voids. Again the same similar pattern follow பண்றோம். Similar pattern will be followed. But here we are getting O-shaped voids. O-shaped voids. Tetrahedral voids are T-shaped voids. Octahedral voids are O-shaped voids. Okay, that's just for understanding how easier. Now you can place it. So how will you assimilate? 1 2 3. 3 blue color atoms. Let them take this blue color atom 1. Sorry, this I will take. So this blue color atom 1 2 3. 3 blue color atoms. 1 2 3 I have taken, and that will be placed. What is that? Yeah, I can't take it in corner. Yeah, I can take, suppose if I'm taken this 1 2 3. Likewise on this top we have 3 red color layers of it, star like voids. 1 2 3. So I can place like this 1 2 3. Is that clear? So still it has some empty space. White color is there between all the 6 particles. Is that clear? If all the 6 particles are arranged in a staggered manner, still some empty space is there. That empty space is called octahedral void. This octahedral void is placed in between 6 atoms. Is that clear? கண்ணா அது புரியுதா? நம்ம ஏற்கனவே பார்த்தோம் இல்லையா? அதேதான் பாருங்க. ஃபர்ஸ்ட் ஒன்னு இப்போ என்ன பண்ண போறேன் அப்படின்னா ஒரு 5 ஆட்டம் எடுத்துக்கோ. 1 2 3 4 5. So here also 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Totally 15 voids இருக்கு. 15 voidsல நம்ம லேயரை க்ளோஸ் பண்ணனும். எது க்ளோஸ் ஆயிடுச்சு? டெட்ராய்டல் void க்ளோஸ் ஆயிடுச்சு. கரெக்ட்டா? Tetraidal voids are getting closed. What about octahedral void? Octahedral void na enakana? You know that one blue color particle, one blue color particle, one blue color particle. You assume that. So this is one blue color particle. Where I can take here. So one blue color particle, one blue color particle. So this is what one blue color particle, and this will be attached like this. Okay. 3 blue color particles சேர்த்துட்டேன். அதுக்கு மேல என்ன பண்ண போறேன்னு பாருங்க. 3 ரெட் கலர் பார்ட்டிகல் இந்த மேனர்ல அரேஞ்ச் பண்ணு. அப்ப 1 2 3. இன் பிட்வீன்ல என்ன இருக்கு? எம்டி ஸ்பேஸ் இருக்கு. அப்ப இந்த எம்டி ஸ்பேஸ்ல என்னது? ஆக்டாஹெட்ரல் வாய்ட். இஃப் யூ அஸ்யூம் இட், இப்ப இந்த இதுல வச்சு பாத்தீங்கன்னா 1 2 3 ப்ளூ கலர், டாப் ஆஃப் திஸ் ஐ கேன் ஹேவ் ரெட் கலர். ஓகே, அப்ப இந்த வாய்டுக்கு பேர் என்ன? ஆக்டாஹெட்ரல் வாய்ட். புரியுதா? புரியல? புரியுதா? இன்னும் கஷ்டமா இருக்கா?
Sir, I have a doubt, sir.
Yes.
In tetrahedral void, we take one red particle, right? So here we are taking 3.
Yeah. Here also we are taking both blue and red particle also. The packing is different. Packing methodology is different. Here in tetrahedral voids, I can pack like this. But octahedral voids also, the packing will be like this. Here I can place only one atom to close the tetrahedral void. But here I can place 3 atoms to place octahedral void, close octahedral void. But even though there will be octahedral voids are there. Is that clear?
Yes, sir, it's clear.
Still we have some empty space in between them. That empty space is called octahedral void. If you assume at any atoms, any of this one, so you consider this is a 1 2 3 atoms I have taken. Suppose red color atom we can't visible, so I can take blue color, black color. So here 1 2 3 atoms. So this is what we are having. So blue color atom you consider this is a black atom. 1 2 3 we have. So this is 1 2 3. This is first atom, second atom, third atom. First atom, second atom, third atom. Above which we are going to place a layer like this. 1 2 3. 3 red color layer will be like this. So if I'm placing the red color layer like this, 1 2 and 3. Still we have some empty space in between. Still we have some empty spaces in between them. In between that we have some empty space. This empty space is called octahedral void. So here also the similar pattern. So if you take an hexagonal packing, it contains both tetrahedral void as well as octahedral void. It consists of both. Suppose if you consider this atom, this is 1 2 3, and here top of this one. So this is a tetrahedral void. That is what this place is called tetrahedral void. This place is called tetrahedral void. That is what these are all the tetrahedral voids, and these are all octahedral void. Is that clear?
So in octahedral voids, tetrahedral voids are blocked, sir.
Octahedral voids? Sorry.
That tetrahedral void places are blocked, sir. Like that we can stay.
Yeah, definitely. It will block. Definitely it will block. Okay.
Okay, sir.
So it consists of tetrahedral voids as usual octahedral void. So totally how many voids? Suppose if I am taking 5 atoms, how many voids are there? There are total 15 voids. Am I right? Out of which 10 tetrahedral voids and 5 octahedral voids. Is that clear? Which means that if I'm taken n atoms, 2n number of tetrahedral voids are there. Suppose n atom, if I'm taken, n octahedral voids are there. This is the important formula to note it off. Okay. Suppose if I'm taken 5 atom, so I have 10 tetrahedral voids and 5 octahedral voids. Suppose 6 atoms, 12 tetrahedral voids, 6 octahedral voids, like that. Is that clear?
Yes, sir. Understood.
Fine.
Yes, sir.
Fine. Super. And next one is the same thing. So blue color atom, 1, 2, 3. So let I'm placing like this. You assume it. These are all the tetrahedral and octahedral voids. Suppose if I'm arresting, these are all the T-shaped voids and these are all the O-shaped voids. Okay. So the T-shaped voids and O-shaped voids. Can you able to imagine this? T-shaped voids and O-shaped voids. T-shaped voids are called tetrahedral voids. O-shaped voids are called octahedral voids. We know that if I'm taken 5 atom, 10 tetrahedral voids and 5 octahedral voids. Okay. Yeah. Suppose in hexagonal packing, if third layer fills AB, if third layer fills up tetrahedral void, if third layer fills tetrahedral void, then what type of arrangement of crystal is like that? AB type. So what is it AB? So let us discuss. So first layer, this is called A. The entire blue color is called A. Red color is called B. And what about the third layer? Where the tetrahedral voids are there now? Now where you are looking tetrahedral voids? In this red color, where you are looking tetrahedral voids? Tetrahedral voids are already told you it's a T-shaped void. Am I right? So these are all the tetrahedral voids. These are all the tetrahedral voids. If you assume with that same manner, so you'll get a tetrahedral void. Is that clear or not? This is a tetrahedral void. So 1, 2, 3 blue atom, out of which 1 red color atom is placed. So the spaces in between them are called tetrahedral voids. Is that clear?
Sir, that white spaces are octahedral, sir.
White space is octahedral. Very nice. That's it. Okay. If third layer fills tetrahedral void, where is the tetrahedral void? The T-shaped void. These are all tetrahedral voids. Am I right? Behind that T, what color is there?
Blue color.
Blue color is there. So then, if I want to close the void I close பண்ணனும்னா என்ன color கொடுக்கணும்? Same
White.
layer, that is blue color. Okay. Now, where you are looking tetrahedral void? Where is the tetrahedral void? It's an inverted T-shaped void. Here you can look at these are all the tetrahedral void. Am I right? This is a inverted T-shaped voids. Also tetrahedral void. If I want to close the tetrahedral void, நான் என்ன color can I use பண்ணணும்? Very simple.
Red, sir.
முன்னாடி பாத்தீங்க டெட்ராஹெட்ரல் வாய்டுக்கு பின்னாடி ப்ளூ கலர் இருந்துச்சு. அப்ப அந்த வாய்ட் அந்த பிளேஸ் அந்த எம்டி ஸ்பேஸை க்ளோஸ் பண்ணா என்ன பண்ணோம்? திருப்பி ஒரு ப்ளூ கலர் போட்டா க்ளோஸ் ஆயிடுச்சு. இப்போ இங்க ரெட் கலர் தான் வாய்ட்ஸா இருக்கு. அப்ப நான் என்ன க்ளோஸ் பண்ணனும்?
Using red color.
Red color again. Now we can see blue color empty spaces. So if suppose if I'm having tetrahedral void like this, இங்க T-shaped void, இது tetrahedral void னு வெச்சுக்கோங்க. அப்ப இத க்ளோஸ் பண்ணனும். அடுத்த லேயர் என்ன பண்ணனும் நானே? ப்ளூ கலர் தான் க்ளோஸ் பண்ணனும்.
Blue color.
புரியுதா?
Yes, sir.
Fine, super. And next one is if third layer fills octahedral void. This is very, very important. If the third layer fills octahedral voids. Octahedral void. What you have to do? So this first layer A problem illa. Second layer B Now the tetrahedral void. Where is the tetrahedral void? That white color space is called
White
tetrahedral
space.
void, O-shaped void. Am I right? This is tetrahedral
Yes,
void.
sir.
If I want to close it, behind that, edavadhu color irukka?
No, sir.
Nothing. So we are in need of new layer to close the tetrahedral void. Sorry, octahedral void. The octahedral void close பண்ணனும்னா what you have to do? ஒரு new layer கொண்டு வரணும். அந்த new layer தான் யாரு? Black color. Now, இப்ப octahedral voids எங்க இருக்குன்னு பாருங்க. என்ன கலர்ல இருக்குன்னு பாருங்க.
Blue color.
Very nice. அப்ப blue colorல இருக்கிறது தான் என்னது? இங்க octahedral void. Is that clear? இப்போ நான் ப்ளூ கலர் அப்ப என்ன க்ளோஸ் பண்ணனும் தேர்ட் லேயர் ஃபோர்த் லேயர் அகைன் ப்ளூ க்ளோஸ் பண்ண என்ன தெரியுது ரெட் கலர் octahedral voids. Is that clear?
Sir, but here the black color is the tetrahedral void, no sir?
Black color is a tetrahedral void. Yes.
Okay.
Now we are talking about we are going to place only third layer fills octahedral voids. Okay. அந்த black color வந்து tetrahedral void தான். நம்ம ரெட் கலர் தான் பார்க்கணும். octahedral void தான் பார்க்கணும். octahedral voidல என்ன இருக்கு? ரெட் கலர் இருக்கு. இப்போ ரெட் கலர் லேயர் க்ளோஸ் பண்ணனும்னா அகைன் என்ன பண்ணும்? ரெட் கலரை கொண்டு வரும். இப்போ ரெட் கலர் வந்ததுக்கு அப்புறம் octahedral void என்ன இருக்கு? black கலரா இருக்கு. Am I right?
Yes, sir.
Yes, sir.
இப்போ நான் இத க்ளோஸ் பண்ணனும்னா அகைன் black கலர். இப்படியே பண்ணிட்டே போறோம். அப்படியே கண்டினியூ ஆயிட்டே இருக்கு. ஓகே. If third layer fills octahedral void அப்படினா this is A, this is B, this is C. So again this is A, this is B, again this is C. ABC type of crystals. Okay. So hexagonal arrangement, 3 dimension. So it is if third layer fills octahedral void, then it is called ABC type. Here also the coordination number is 12. Coordination number 12 தான் பண்ணாங்க. சரிங்களா? இது புரியுதா? இது புரியுதா இல்லையா? Very very important. அப்ப cubic close packed structure எப்படி இருக்கும்? இதுக்கான இது ஃபர்ஸ்ட் லேயரா, இது செகண்ட் லேயரா, இது தேர்ட் லேயரா, இது அகைன் ஃபர்ஸ்ட் லேயர். பாருங்க. So first layer, second layer, third layer, again first layer. 1 2 3 1 2 3, which means that ABC. Okay. Now we can have octahedral void. எப்படி இருக்கும் பாருங்க. 1 2 3 4 atoms. One atom will be in top, one atom will be in bottom. This blue color. So if you connecting all those things, you will get octahedral voids in between that 6 atoms. அப்ப இந்த இடத்துல இருக்கும். கரெக்ட்டா? So எந்த ஸ்பேஸ்ல இருக்கும்னா, so the octahedral voids will be located like this. இந்த இடத்துல என்ன இருக்கும்? void இருக்கும், empty space. சரியா? இது புரியுதா? இது cubic close packed structureல நடக்கக்கூடிய விஷயம். அப்ப locating tetrahedral voids. It's very very important. Location of tetrahedral voids. How to find out a tetrahedral void? எப்படி கண்டுபிடிப்பீங்க? So assume it is in crystal. In crystal, suppose one corner atom is here. So one corner atoms will be arranged like this. Okay. Now we can get a tetrahedron shape. Okay. So in between that we have some empty space here. This empty space is called tetrahedral void. Am I right? So how many corner atoms are there for this cube? 8 corners. So 8 tetrahedral voids will be there. I'll explain you again. So here one atom is here, one atom is here, one atom is here, another atom is here. Now in between 1 2 3 4 atoms we have some empty space. This empty space is otherwise called as voids. Are you able to understand this? This empty space between the 4 atoms are called the voids. That voids are called tetrahedral. Is that clear or not?
Sir, so number of corner atoms is equal to number of tetrahedral voids, sir?
That's it. That's what I'm telling you. N atoms are there, which means that how many tetrahedral voids are there? 2n tetrahedral voids. Okay. Let us check how 2n tetrahedral voids are there. Okay. How many corner atoms? 8 corner atoms. Am I right? So here 1 2 3 4 5 6 7 8. There are 8 corner atoms are there. One corner atom contribution is 1 by 8 plus 6 face-centered atoms are there. One face-centered atom contribution is 1 by 2. So totally how many atoms are present in this particular unit cell? 4 atoms, because it is a face-centered unit cell, am I right? In this face-centered unit cell, total number of atoms are what? For unit cell, particular one unit cell, it is 4 atoms. But how many number of voids? Each corner we have one tetrahedral void. So totally 8 corners are there. One corner, one void. Okay. So 8 corner, 8 voids. Okay. But the number of atoms are 4, number of voids are 8. That is what n atom if we taken 2n number of tetrahedral voids we can get it. So we assumed in the previous slide, as 5 atoms we have taken 10 tetrahedral voids are there. Is that clear? Is that clear or not? Purida, Purilia.
Yes.
புரியுதா? Number of atoms பார்க்கணும். Total number of atoms எத்தனை இருக்குன்னு பார்த்துட்டு எத்தனை void இருக்குன்னு கண்டுபிடிச்சா முடிஞ்சது. So எத்தனை void இருக்கும்? So total 8 corner atoms. So 8 voids இருக்கும். That's it. Okay.
Sir, to find the number of atoms, why are we not taking that ECC, sir? Because it is normal cube only, no, sir.
This is a hexagonal packing, na? Hexagonal packing means face centered.
Okay, sir.
Locating octahedral voids. Here there are 2 type of octahedral voids. So one is by, so you can assume that one is by body centered atoms. That means a body at the body center of the body we are getting formed one void, and edge centered, through the edge centered we are getting 3 voids. Totally by the body centered we got 1 void, and edge centered through which that we have 3 voids. Total number of voids are what? 4 voids. How many number of atoms are there? N number of atom means n voids are there. Am I right? Here for this particular unit cell, 4 atoms are there. So it will give 4 voids. 1 from body centered, another 3 from edge centered. Let us check how it will come. So this is by octahedral void at the body center. That means the center of the body we have some empty space. That's it. Okay. That can be given by face-centered atoms. Now we can assume it here. Just a minute. Yeah. So the face-centered atoms, through the face-centered atom, we are getting created a void. Now this is a tetrahedron. 6 atoms are there. 1, 2, 3, 4, 5, 6. 6 atoms are there. In between all the 6 atoms, we have some empty space. This empty space is called void. So in between all the 6 atoms, it will be called as octahedral void. Is that clear? So in between all the 6 face-centered atoms, some empty space is getting created. So now we have an empty space here. That empty space is called the octahedral void. Is that clear? So how many voids we can get it? Only 1 void. Because face-centered atoms, only 6 atoms are there. For particular 1 unit cell. For particular 1 unit cell we are talking about. Okay. Is that clear?
Yes, sir.
An octahedral void at the edge center. This is somewhat difficult. So face first corner atoms. How many corners? 8 corners. If another unit cell is attached like this, here also that unit cell also has 8 corner atoms. Okay. Bottom of this we have some corner atoms. Yes, we can have like this. Okay. Now we can have face-centered atoms. How many faces? 8 faces. 6 faces. 1, 2, 3, 4. And back of this, front of this one. Likewise, this unit cell also has similar pattern. This unit cell also has some similar pattern. Now, what is the meaning of edge centered? What is the meaning of edge centered? What is the edge centered? Edge means what?
Vertices, sir.
This is one edge, am I right? This is one edge. Is that clear? One edge. How many edge for the cube? How many edges are there in a cube?
8.
1,
8, sir.
2, 3, 4. 4 edges. 5, 6, 7, 8, 9, 10, 11, 12. Over line or edge. Each and every line is an edge. Okay. So edge. There are 12 edges on it. It's an edge. 12 edges. So there are 12 edges are there. Suppose if nearby unit cell attach ஆயிருக்கும் 1 பக்கத்துல மேல இப்படி இருக்கும். அப்போ நான் என்ன அசியூம் பண்றேன் அப்படின்னா, if I'm assuming this edge இந்த எட்ஜை மட்டும் ஞாபகம் வச்சுக்கோங்க. இந்த எட்ஜை மட்டும் பார்த்துக்கோங்க, வேற எதையும் பார்க்க வேண்டாம். இது இப்ப எத்தனையோட ஷேரா இருக்கு? 2 யூனிட் செல்லா ஷேரா இருக்கு. ஹாஃப் ஷேரா இருக்கு. இப்போ 3 யூனிட் செல்லோட ஷேரா இருக்கு. இப்போ 4 யூனிட் செல்லோட ஷேரா இருக்கு. ஒரு ஏஜ் it is shared with 4 different unit cells. Am I right? ஒரு எட்ஜ் வந்து 3 டிஃபரெண்ட் யூனிட் செல்லோட ஷேர் ஆயிருக்கு. அதனால டோட்டலா ஷேர் என்ன சொல்றோம்? 4 அப்படின்னு சொல்றோம். புரியுதா? There are 12 edges. 12 edges are there. The void is called as edge centered. What is the edge center? This is a edge. Correct? இதான் edge. இந்த edge உடைய சென்டர்னா எதுக்குனா? Center part of this. This is a center part. It's an edge center. Okay. So if you assume that this is an edge. இந்த edgeல centerல ஒரு void create ஆகும். Octahedral void create ஆகுது, which means that 6 atoms are combining and it forms in between them some empty space. What are all the 6 atoms? 1, 2, 3, 4, 5, 6. 6 atoms are there. Is that clear? Suppose if you consider this edge center 1, 2, 3, 4, 5, 6. 6 atoms are there. Is that clear or not? அப்ப ஒரு எட்ஜ் சென்டர்ல ஒரு void கிரியேட் ஆகுது because of 6 particlesனால, 6 atomsனால. இங்கே ஒரு void கிரியேட் ஆகுது. இது பேர் empty space. All the atoms in the fashionல அரேஞ்ச் ஆச்சுன்னா it forms one void in between the center of the edge. So அப்ப எத்தனை edge center void form ஆகணும்? புரியுதா இல்லையா? எட்ஜினுடைய சென்டர்ல because of the surrounding 6 atomsனால they form octahedral structure, octahedral void. அப்ப இந்த இடையில என்ன ஆகும்? ஒரு empty space create ஆகும் because of the 6 atomsனால. அதனால தான் இது பேர் என்ன? octahedral void. புரியுதா?
Yes sir, understood.
Yes sir.
Okay. How many edges கண்ணா? எத்தனை edges இருக்குன்னு பார்த்தோம்? 12 edges ன்னு பார்த்தோம். கரெக்ட்டா? Okay. இப்ப ஒரு எட்ஜ் எத்தனை யூனிட் செல்லோட ஷேர் ஆகுதுன்னு பார்த்தோம் இங்க.
6.
ஒரு எட்ஜ் how many யூனிட் செல்லோட ஷேர் ஆகுதுன்னு பார்த்தோம்? 3 other unit cell. அப்ப டோட்டல் அதோட சேர்த்தா 4 யூனிட் செல். அப்ப 12 into 1/4. அப்ப ஒரு எட்ஜ்ல ஒரு எட்ஜ் சென்டர்ல ஒரு void ஃபார்ம் ஆகுதுன்னா அப்ப அந்த எட்ஜே 4 டிவைடா இருக்குன்னா அந்த void என்ன இருக்கும்? 4 டிவைடர். கரெக்ட்டா? அப்ப 12 into 4 எவ்வளவு கணக்கு கிடைக்கும்? 3 voids. புரியுதா? 3 voids கிடைக்கும் டோட்டலா. புரியுதுங்களா? அப்ப எட்ஜ் சென்டர் மூலமா 3 voidsம் பாடி சென்டர்ட், அதாவது ஃபேஸ் சென்டர்ட் ஆட்டம்ஸ்னால என்டையர் பாடியில இங்க கிரியேட் ஆச்சுலையா, இங்க கிரியேட் ஆச்சுலையா, இதுக்கு பேர் என்ன? இது ஒரு ஆக்டாஹெட்ரல் வாய்டும் கிடைக்கும். அப்ப இங்க ஒரு ஸ்பேஸ், இங்க 1 2 3 3 ஸ்பேஸும் கிடைக்கும். சரிங்களா? டோட்டலா 3. ஒவ்வொரு எட்ஜ் சென்டர்லயும் ஒரு வாய்டு கிரியேட் ஆகும். பட் ஒரு எட்ஜ் எத்தனையா ஷேரா இருக்கு? 4 டிவைடா இருக்கு. அப்ப ஒரு வாய்டு 4 டிவைடா இருக்கு. அப்ப 4 டிவைடா இருக்குன்னா என்ன பண்ணுவோம்? 12 edges not 12 divided by 4 போட்டீங்கன்னா எனக்கு கிடைக்கும் 3 voids total. புரியுதா? அப்ப edge center மூலமா 3 voids, then body center, that means face center atoms மூலமா 1 void, total one number of voids are what? 4 voids. 4 voids, 4 octahedral voids. 4 octahedral voids. If suppose if you taken n number of atom, n number of voids are there. Why? Because how we calculate n number of atom? Because it is FCC. FCC means number of atoms are 4. Okay, number of atoms are 4. 4 atoms, 4 voids. Is that clear? This is what
So
I get.
3 edge-centered voids are there per unit cell, sir.
Sorry,
Yes.
sorry.
3 edge-centered voids are present per unit cell.
Yes, yes.
And then one extra is there due to it being FCC.
One extra is there due to body centered atoms.
Because it's FCC.
Yeah.
Okay, sir, understood.
Because of body centered atoms, we have one category, one void. Through that edge centered, we have 3 voids. Totally, we have 4 voids. Suppose if
Okay,
you
sir,
take
understood.
4 number of atoms, 4 void octahedral voids are there. Okay.
Okay, sir.
Okay, Kana. We'll stop with this. We'll see you next week. Okay, fine. Thank you.
Thank you, sir.
Thank you, sir.
Yes, sorry, ma. Hello.